So in this video, we will talk about the deviation through a prism of small angle. For that, let me draw a triangular prism like this. Let this be a triangular prism with angle of prism, let's take that as A. Okay, now at this point, let me draw a incident ray. That incident ray will hit at the point, this point, and let me draw a normal at this point. It will be like this. Okay, normal will always be perpendicular to the surface. Let's call this point as T, this point as U. Let's call this as V. That is, this normal, let's name that as N dash, will be perpendicular to the refracting surface TU. And when the light, see, this is the rarer medium, and the glass prism is obviously a denser medium, and here also it is rarer. So when light travels from rarer to denser medium, it bent towards the normal like this. Okay, we already discussed this in the last section. If you have any doubt, you can go back and check that video. And there is one more. Let's name this point as some P. Let's name that as P. Now let's call this point as Q. I have to draw a normal in here also. Okay, so this time the ray is traveling from denser to rarer medium. So it bends away from the normal like this. Okay, so this is the emergent ray and this is the incident ray. And we can take this as angle of incidence. Let's name that as I1, the angle between the incident ray and the normal. And this is the refracted ray, that is PQ is the refracted ray, and the angle between the refracted ray and the normal, we can take that as angle of refraction. Angle of refraction at the first surface, to be specific. Now at this point we can take that as R2, but R2 here is the angle of incidence at the second surface. See, TV is the second surface, so R2 become the angle of incidence at the second surface, and we can take this as angle of emergence, or otherwise angle of refraction at the second surface. Clear? Now we know applying Snell's law, at the point, let's say at point P, we know Snell's law is like this: sine of angle of incidence. Here the angle of incidence is I1 by sine of angle of refraction. Here the angle of refraction is R1 equal to, see, this ray is moving from rarer to denser medium. That is, it is moving from air to glass. So we have to take the refractive index of glass with respect to air. That is refractive index of glass with respect to air. We write it like this: mu of G with respect to A. Since it is moving from air to glass, so we have to first consider the second medium. That is, this is equal to refractive index of glass, absolute refractive index of glass by absolute refractive index of air. We know mu21 will be mu2 by mu1, the absolute refractive index of second medium by absolute refractive index of first medium. Also, for small angles, we know sine I approximately sine I1 approximately equal to I1 itself, and comma sine R1 approximately equal to R1 itself. Clear? That is for small angles. Okay, so I can rewrite this equation as, instead of sine I1, I can put I1 by R1 is equal to mu of glass with respect to mu of air. Now we can take the refractive index of glass as mu itself, and refractive index of air is 1. So here mu g represent, mu g is also mu, which is the absolute refractive index of glass. Clear? But for air it is 1. So I1 is equal to mu into, take this R1 to the right, mu R1. Okay, by 1 it's 1 is mu R1 itself. Okay, this is actually equal to mu. Okay, so this is the first equation. Now let us apply the Snell's law at the point Q, or at the second surface. That is, applying Snell's law at point Q. This time the angle of incidence is R2. So I have to write sine of angle of incidence, that is sine R2, by sine of angle of refraction. Here it is angle of emergence also, I2. See, this is the angle of refraction, that is same as the angle of emergence, equal to, this time it is moving from glass to air. Is that clear? Now it is moving from denser to rarer. So I have to first consider the second medium. Here it is air. So refractive index of air with respect to glass. Like I said before, it will be absolute refractive index of air by absolute refractive index of glass. And we know for small angles, sine R2 is approximately equal to R2, and sine I2 is approximately equal to I2, which is equal to mu A, we know that is 1, and mu G, we took that as mu. Implies I'll get mu R2, taking this mu to the left, and I2 to the right is equal to I2. That is, I2 will be mu R2. Clear? Let's take that as equation number 2. Now we know, we already derived this. The relation between deviation and angle of prism is like this. We have deviation delta is equal to I1 plus I2 minus A. Here delta stands for deviation. We already derived this expression in our last video. If you have any doubt in its derivation, you have to visit that video. You first have to know how this equation is derived. Okay, so delta is equal to, here I1 is actually mu R1. So mu R1 plus I2 is mu R2. Sorry, mu R2 minus A. So delta will be mu times R1 plus R2. I can take the mu outside, minus A. Also, we know angle of prism will be R1 plus R2. This is also in that video. We already derived this. Okay, angle of prism will be R1 plus R2. So I can replace this R1 plus R2 with A. So delta is equal to mu A minus A. That makes delta is equal to mu minus 1 times, I can take the A out. So this is the expression for angle of deviation for small angles. Delta equal to mu minus 1 into A. Clear? Now we need to find an expression for angular dispersion. Angular dispersion, it's usually represented by delta. Okay, so what actually is this angular dispersion? For that, let me take a prism again. Okay, so this is a prism, and this is the refracting phase. Let this angle be angle A, that is the angle of prism. So what happens when I pass sunlight through this prism? Actually, sunlight is usually a white light, but when it enters to a prism, the sunlight will get split into its component colors. Like there will be, you can see red on the upper region and a violet on the lower region. And this splitting of composite light is the sunlight into its component color, is called dispersion. So as you can see from the figure itself, the deviation for the violet and deviation for the red are different. Clear? This is the red light, this is the violet light. Clearly violet deviates more than red because red has a greater wavelength. So when wavelength is greater, deviation will be less. Okay, so red has higher wavelength, so it deviates less. Clear? So these are the two extreme colors or extreme wavelengths for sunlight. So angular dispersion delta basically means the deviation for violet light minus deviation for red light. Okay, so this is called the angular dispersion. But we derived delta is equal to mu minus 1 into A. Okay, so delta V will be delta V is equal to refractive index for the violet light minus 1 times A. Angle of prism remains the same for both this light. And for red light, see clearly for different colors, the refractive indices for prism is different. Refractive index for the prism is different. So for red light, we can take mu r minus 1. Mu r stands for the refractive index of prism for the red light times A. So this will be, when I plug in these two values in here, it will be mu v minus 1 times A minus mu r minus 1 times A. So this will be, I can take the A out. So this will be mu v minus 1 minus mu r minus 1 times A, since A is common for both these terms. So expanding, I'll get mu v minus 1 minus mu r. This minus and minus will become plus 1 into A. I can cancel this one. So delta angular dispersion is actually mu v minus mu r times A. So this is the expression for angular dispersion. Now there is one more term called dispersive power. Dispersive power. It's usually represented by omega. See, for this light, the mean light is actually a yellow color. That is, in between this violet and red, we have green actually for VIBGYOR. Or this green is the mean color, but usually we take yellow as the mean color. There are specific reason for that. I'm not discussing it in here. You just take yellow as the mean color. Okay. So dispersive power is actually, by definition, the angular dispersion is omega equal to the angular dispersion by the mean deviation. Mean deviation. Mean deviation actually means the deviation for the mean color. Here it is yellow. Okay. So angular dispersion is mu v minus mu r into A by, for mean color the deviation is yellow, so for yellow color deviation for yellow color is equal to refractive index of yellow color minus 1 into A. So substituting in here, it will be refractive index for yellow minus 1 into A. So for mean deviation means the deviation for the yellow color. So cancel this A and A. So you will get angular dispersion omega is equal to mu v minus mu r divided by mu refractive index of yellow minus 1. Clear?